All right, so let's take a closer look at problem 3, in particular parts A, B, and C. Part A is this thing about the Thevenin equivalent. Part B is getting the initial conditions you need to solve your differential equation that you're going to develop and write in C. Okay, part D then gets into sort of the numeric solution of that differential equation. But in part C, we kind of work backwards a little bit, right? What I want to do is I want to try to explain the problem in a way that may be a little bit more clear for you, right? So the circuit that I was talking about is this circuit here on the left, where I called this combination of this thing, the transistor and the resistor here, that was an inverter, right? So we said that what happens is when I put a high voltage here, so I put 5 volts at VN1, then this switch here, this transistor turns on, right? And so that makes this voltage go low. V out 1 goes low. All right, so we're going to try to sort of understand that a little bit. What happens, we said, is this transistor can be modeled as this combination of this resistor here, R on, and a switch. Okay, so what I'm telling you here in particular, if I look at parts B and C, in part B, I make the statement to say that assume that VN1 has been low for a long time. So when VN1 is low, that means the switch here, switch is open. And when VN1 is high, that means the switch is closed. Okay. So what we're saying is really in problems in parts B and C, what we're saying is that time t equal to 0, this is the way to think of it. At time t equal to 0, this switch right here is closing, right? I'm saying VN1 has been low for a long time, meaning the switch was open for a long time, okay? And at time t equal to 0, what I'm doing is I am bringing VN1 high, which is closing the switch. So at t equal to 0, I am closing the switch in the circuit on the left. All right, so basically what I'm saying is you got to write a differential equation to solve for the capacitor voltage in the situation where this switch was open for a long time, right, and is now closed. So if I look at part B is saying, okay, I have this circuit here, resistor, and the switch has been open for a long time. So I have an open circuit down there. And then I have L and C. Okay. So this is V sub C or VN2. This is I sub L. This here, the voltage across this series combination of the resistor and the open is V out 1, right? V out 1. Okay. So in this case, right, when I say the whole thing of the switch has been open for a long time, that means we have reached steady state, right? My definition of steady state, when I'm talking about DC circuits like this, and that's what this is, a DC circuit, that means all of the derivatives, DIL by dt and dVc by dt, are equal to 0, right? Those things are equal to 0. And so at that point, if those things are equal to 0, that tells me all my currents and voltages are constant. Okay, so effectively then, if I look at this particular circuit, right, so what I have to do is when I look at the circuit, I can say, okay, well, I can replace the capacitor with an open, I can replace the inductor with a short. So basically I have this situation, I have this and this. Okay, so it's fairly easy to solve for V sub C and I sub L. I sub L clearly has to be 0 because it is basically the current through an open circuit. Now, the thing that causes people problems here is, so my way of looking at this is saying, all right, well, give me a Thevenin equivalent circuit that replaces everything to the left of this dashed line here. Okay, so in other words, reduce this circuit to a Thevenin equivalent and if I go back to what I had originally, right? I had an inductor and I had a capacitor. What I'm saying there in part B, I'm saying, okay, well, here is the terminals, right? This was my Thevenin equivalent. This is V out 1. Okay. This is my R Thevenin. And now at those terminals, I'm going to have an LC. Okay. And I solve for this assuming steady state again. Right. So what you have to do here is again, so if I'm in steady state, what does that mean? Well, that means this guy is a short and this guy is an open. And I have to solve for all of the voltages and currents that I asked for in that particular circuit. But what I'm doing is I'm saying I got to replace everything to the left of that dashed line with that Thevenin equivalent. Now in part C, so again, what comes out of part B is really what I need for my initial condition. So the thing I'm really getting out of it is what is I sub C of 0, right? What's the initial capacitor current and what is the initial capacitor voltage, V sub C of 0, or as I'm calling it in this problem, Vn2 of 0. Right, I sub C of 0 gives me C dVc dt of 0. That's really what I'm getting at in part B, is to get those initial conditions I'm going to need later to solve for everything. Now, so if what I'm saying is in part C, this switch was open for a while, so we got the initial conditions we developed in B. Now I'm saying I'm going to close this switch. So when I close the switch, so in part C, I close the switch. So then I have 5 volts, my 900 ohms, my 100 ohms, my inductor, and my capacitor. That's a very difficult circuit to write because I've got 2 meshes. It's hard to write a differential equation with something like that. So this is V sub C equals Vn2. This is I sub L. So when I look at this again, it's the same thing. The voltage across this resistor here is V out 1. And I'll move the 100 ohm over here. What I'm saying is I want to create a Thevenin equivalent for everything looking that direction. So at the terminals right here, so if these are the terminals, I'm saying what I want to do is I want to replace everything to the left of that with a Thevenin equivalent, where this is a V Thevenin and an R Thevenin. And then at the terminals there, I have connected an L and a C. Now, the other video talks about how to approach developing the differential equation for this, but you should be able to say, okay, well, that means I need to figure out how is it that I develop a Thevenin equivalent for everything to the left of that dashed line. So meaning that if I said to you, here's 5 volts, and here's 900 ohms, and here's 100 ohms, a Thevenin equivalent basically says replace this circuit with an entirely equivalent circuit from the perspective of these terminals. So something where I have another voltage source and a single resistor. This is a really powerful theorem when we're doing any kind of real electrical design. Okay. So in this case, what I do is I say, well, if there was nothing connected to the terminals, what would the voltage be at open circuit? So what would the voltage be that I would see here? Then the second question would be, well, if there was actually something connected and there was a current flowing out here, where would that current flow in this circuit? Well, to do that, you think of it using the principle of superposition and you turn off the voltage source inside this thing. You turn off that 5-volt source. And what you see is a current at the terminals would flow through the parallel combination of those 2 components. So this circuit here and this circuit here are equivalent from the perspective of their terminals. And it's pretty easy to show that if what you do is you say, okay, well, if the current was 0 here, what voltage would I get? If the current was 0 here, what voltage would I get? The voltages you would get would be the same with 0 current, okay? If I kept increasing the current, so if I put this at 1 amp and I put this current at 1 amp, well, the voltage I would see at these terminals and the voltage I would see at these terminals would be the same. That's the idea of a Thevenin equivalent circuit. Those two circuits are equivalent from the viewpoint of their terminals, meaning with the same amount of current flowing out, the voltage you would see would be the same. Okay, that's our way of kind of analyzing these circuits.